course overview, starting with the question, what's the internet, right? Today we're going to delve a little deeper, still staying at the chapter 1 level, which is a 10,000 feet overview, like I said, with the primary goals of familiarizing ourselves with a lot of terminology we'll see later in the course, as well as some high-level concepts that pervade across all the different layers, right? I got a request from some students saying the microphone wasn't very clear the last time. The volume right now is at the max. Can people behind hear me okay? Okay, I'll try not to let my voice trail. I sometimes tend to do that. I'm sorry about that. So today we're going to delve a little deeper, like I said. We'll look at network structure, edge networks, or the edge, access networks, network core, and so on. And you hear? That's not me. Okay, that's okay. Can't do anything about it. Sorry. Where was that? Network structure. We'll learn about a very important distinction between network designs, two network designs, two fundamentally different network designs. Packet switch networks versus circuit switch networks, or rather, packet switch networks like the internet versus circuit switch networks that's been around for longer and used to underlie much of telephony for all of the previous century, right? And it's even now continues to some extent, to a good extent. All right, so we started out with this question of what's the internet. We looked at a nuts and bolts type of view. Sorry, one slide back. Where you could decompose the internet structurally, sort of hardware structurally into edge computers, packet switches, or routers, links connecting those that are organized as a network of networks. We also saw further that this nuts and bolts view could extend into to encompass some of the software aspects of it, like protocols or request for comments, RFC documents, that are governed by IETF, or the Internet Engineering Task Force, that specify what a protocol ought to be. So I gave you an example of a protocol. What's a protocol? It's just a convention. It specifies the syntax and semantics of messages that are going to be exchanged, right? So just like we have a hello, what's the time kind of a protocol that we saw in class, when a TCP session starts out, there is a handshake involved to establish a connection. When an HTTP, a web request, is made by a computer to the other end, there is similarly going to be not quite a handshake, but a request response kind of a protocol going on there. So that's what a protocol means. It tells you what the messages mean, how they're to be interpreted, and what are typical expected responses, what are error codes if some error or exceptional conditions happen, and so on, right? Okay, there's also a service view that corresponds a little more to the great-grandmother question. Like if she came about and from centuries back and asked you what the internet is, someone said, well, it's a way of communicating. Others might say, well, it's a way of watching YouTube and Netflix online, right? Depending on what all the primary uses of the internet for you. And so that corresponds to what's called as a service view. The internet provides a service. So unlike a network, like a telephone network that provides one type of service, audio calls, the internet is a network that provides a multitude of services. So these are like web or streaming or video, multimedia, and whatnot, right? So you can build a lot of different kinds of applications on top of the same core network. What allows us to do that are these programming interfaces. So you could think of the service view as encompassing also an API, application programming interface, that says, here's how you program with this network. Here's how you attach appliances, just like you do that in electrical grid. Here's how you attach networked appliances into the internet, right? By developing applications using standard APIs. For example, socket programming APIs that we're going to see a little further in the course, right? Okay, so we're going to move on now and look at the network structure in a little more detail, right? The network structure, at a very high level, you could consider as being composed of the edge, access, and core. Okay? What are these? Sorry. The edge constitutes computers like my laptop here right now, your laptops, phones, servers and data centers, web servers. All of these are edge devices that are hanging off of the edge of the network, right? The very last point typically. These are not formal terms. Often there's ambiguity whether something, to what extent something is an edge versus core, and then so on. So we are informally familiarizing ourselves with some terms that we will continue to use informally, right? Access networks are what connect this edge, machines on the edge. Can someone hear a resonating, like,
From the speaker?
yeah, that's bugging me too. So, sorry, I think I have to just reduce the volume a little bit, because that's when, I don't know if this helps. Yeah, I think this is, I can try putting this further away a little bit. I don't think there's a way to ensure loudness as well as completely prevent that. So hopefully this is better. If not, then we just have to wait until the next class for it to get better. Okay, access networks, right? These are what connect the edge to the core of the network. This is how we get, you can think of internet access, this is how we get it. Out here, right now, a Wi-Fi network serves as the access network. At home, a broadband network, let's say a cable modem service provider is going to provide you access, right? On your phone, an LTE or 5G or data plan provider is the one that's acting as the access network. These could be wired or wireless, and we'll spend some time looking at some examples of these in more detail. And the edge is connected via access to the core that consists of larger networks. These are the so-called network of networks. These could be large ISPs or internet service providers like AT&T or Sprint or Dutch Telecom, Level 3. There's many large internet service providers, as well as some tier 2 or regional ISPs that tend to be smaller in size, that may not have global spread, but they provide regional internet service. We'll look at the structure of some of this, and especially a little bit of the economics of some of this as well, right? All of this in chapter 1. Okay, so access networks, they're connecting end systems to edge routers, to the edge of the core, to the edge side of the core of the network. There are different types of access networks. Like we're sort of informally, in real life, familiar with different types of access networks, like cellular or cable modem or institutional access networks and so on. But we're going to look at it we're going to look at examples of these networks with a somewhat more precise technical lens, focusing on those two questions. The two questions being whether it's shared or dedicated, and what is the transmission rate. Transmission rate is a metric that tells you how fast your network is. It's a very specific metric, however. It's measured in bits per second. So when you say I have a 100 Mbps plan that Comcast gives me, you're talking about 100 megabits per second, 100 million bits per second, right? That's the speed. What extent I'm causing this? think I'm going to just try talking without the microphone. Is that better than this? Right. Sorry, you got to pick the lesser of the two evils. I don't know what's happening. I sent them email. I think they've done something, but it seems to have worsened. Okay, so I'll just try speaking louder. We'll put up with that for this one. Okay, two technical questions. The first being shared or dedicated. The second is how fast is it? Where fast is being here specifically measured through this metric called the transmission rate that has the units of bits per second, right? Okay. So here's an example of a network you're all familiar with as users. This is a cable-based access network or a cable modem network. Out here, Comcast is almost a monopoly, but there's other cable modem service providers slowly expanding. There's many other examples throughout the country, throughout the world, of cable modem service providers. These are trying to do what's called a frequency division multiplexing at the end. On top of the same cable, the coaxial cable. A coaxial cable, it looks like the thing that's shown in the picture. It's got an outer cylinder with like a pointy, sharper wire coming through. So you've probably seen this at home if you had cable modem service anywhere, right? What it's doing is it's splitting. The frequency division multiplexing refers to distributing different content on different channels or frequencies. Those TV channels, there are different frequencies. You tune to different frequencies, you get different channels, right? Different programming content. Similarly, you set aside some of those frequencies for transmitting data, not the broadcast TV channels or cable TV channels. So that's how it's working. It's the division multiplexing refers to a resource allocation mechanism that says that okay, these are for this type of content, this is for data. Your wanted to make sure that I'm using the current version of my slides that I have. Okay. So is this shared? So what are the speeds here like? The speeds here, like it says, some of these numbers may be outdated. These are, fairly in the right ballpark. So your download speeds tend to be in the tens of Mbps. It could be 100 more than, it could be hundreds of Mbps. It could be about a Gbps. They are in general significantly large. That depends on your plan, right? In general, you don't have 10 Gbps access networks and cable modems today. Your upload speeds, on the other hand, are much slower compared to download speeds. This is something that's configurable. The cable modem service providers realize that most of us consume or download a lot more content than we upload from our home network. We increasingly upload a lot of content too because of cloud services, right? So when Dropbox is syncing or Google Drive is syncing in the background content that's on your computer with what's in the cloud, it's uploading a lot of information there as well, right? But most of us consume or download a lot more. This also answers one of the Piazza questions, like downstream and upstream relative to what? Well, downstream is download, upstream is the upload direction, right? So that's what's being talked about when you say downstream or upstream here. So the technology here, like I said, is a coax. This is a hybrid fiber coax. So it's both copper and fiber, a hybrid of copper and fiber. Asymmetric speeds, and the question of shared versus dedicated, the answer for cable modem is it's a shared access network. The sharing happens at the granularity of, I see an end there?
Well, what's the difference between transmission rate and bandwidth?
Very good question. What's your name?
Nathaniel?
Nathaniel, yeah, I should have remembered. Nathaniel's question is, what is the difference between transmission rate and bandwidth? For much of this course, we will use those two terms synonymously. Okay? The difference is transmission rate is very specifically measured in bits per second always. I'll show you an example of this. I'm running ahead a little bit, which is it's measured as the size of the packet divided by the speed of the measured distance. That's sort of the defining problem. I'll show you an example of how it relates to what's called a transmission delay. Okay? So it's that very specific metric. What's bandwidth? Bandwidth is a looser term. It can be used more widely. It can be used to mean bits per second transmission rate. It can also be used to mean how wide a band of frequencies you have, which is effectively also measuring how much bandwidth you have in this system. The more cable or frequency spectrum, wireless spectrum you have, it's like real estate. The more of it you have, the richer you are, the faster you are. So bandwidth is a looser term. It can be used in multiple different contexts that all relate to speed via transmission rates. So they're often used interchangeably. At least in this course, we won't really be looking at frequency spectrum definitions of bandwidth. So for all purposes, you can really do these numbers. Good question, thanks. Shared versus dedicated. The sharing, it is shared, like it says. The sharing happens at the granularity of a few households. So it could be a street, it could be a few streets. It really depends on the organization of the modem network itself. And so this is why you may have noticed that as work from home became popular, a lot of people started having cable modem problems during the pandemic because the cable modem networks were not provisioned to handle that much load of everyone working from home. This is also a reason why when everyone wants to watch TV online at the same time, Netflix, YouTube, and online video content, when they come back from work, late evening or late afternoon or evening, that's when the speed sucks often if you have problems, right? And the reason is because everybody is doing the same thing, they're sharing this network. So it's like a shared wired Wi-Fi network here or an Ethernet network, where the bandwidth across all the end users that are sharing that portion of the network, they have to divide the resources amongst themselves, right? So if somebody hogs a lot of those resources, the other people are going to see reduced speed because of that. It's shared only up to this cable head end point, after which there's what's called a switching, where there's dedicated lines going to different portions of the core. Okay. A DSL, this is less common these days than cable modems, but still a very worldwide, as well as in the US, a fairly common means of access network. This tries to double up on the use of a telephone path. So just like cable modems are trying to use existing fiber that's laid out for cable for TV purposes, this is trying to do the same thing with what's the infrastructure that already exists. So you don't have to dig out new holes and run new cables for the internet by using the one that already exists for the phone lines. As before, you're allocating different frequencies for voice for the telephone service versus data. That could also carry voice over IP, but it could also carry all other data, internet service content. The speeds generally tend to be somewhat lower, but as technology trends are improving, all of these technologies are improving the speed. This is a matter of provisioning, it's a matter of upgrading the technology. But, and again, this is like cable modem, DSL, and speeds tend to be asymmetric. So like it says, you can say on the ballpark of these days, tens of Mbps download speeds and, single digit around 10 Mbps ballpark upload speeds in DSL. So a little bit slower than cable modem, but comparable. Okay? A fairly popular means of access. There's also fiber to the home that I'd say between the two is a little more similar to cable modem, but is neither riding on the cable networks, cable TV networks, nor the telephone line. These are just fiber that's being laid out specifically for the purpose of internet access. I don't think the last I checked, I don't think there was fiber being offered in this area, or sort of even in the Cambridge, Boston like area around here. But this is available at a lot of places. cable modem speeds are already catching up to gigabit per second speeds that fiber first was introduced, boasting gigabit per second speeds that were not available with broadband. Broadband is a term that refers to cable or DSL technologies, right? And the distinguishing aspect of this technology is it's completely optical fiber. So the fiber technology is different, and therefore how you encode bits into signals on that, and what the transmission speeds are on that technology, that differs as well, right? And these could again be active or passive networks, where the distinction is whether it's shared. These could be both shared or dedicated. So an active network would be more like a dedicated line, and passive would be shared across the networks. And the speeds tend to be different to actives, mostly are larger networks with higher speeds, and passive more residential access. Right? Okay, so another example of an access network, zooming in a little further, it could simply be a single household. Your home, a typical home, a modern home these days, an internet-connected home these days, is an access network in and of itself, right? How is this access network being organized? So if you think of, let's say, this house getting internet service through cable modem, the cable modem provider or the DSL service provider is going to give you a modem that connects to the central office that at the next step connects to a router. Okay? If you have Wi-Fi, if you set up Wi-Fi at home or a wireless router, that is another distinct component. Often these two components may be combined. Sometimes these two components may be combined if your cable modem service provider also gives you, all three may be combined if your cable modem service provider also gives you a box that has an integrated a router and a wireless access point. People often refer to this thing as a router, okay, the thing that gives you wireless access. Technically, we'll learn a little bit more when we look at the link layer in more detail that this is not a router. A router has to be something that speaks the IP protocol, the internet protocol. It's a level 3 or a network layer device. This is a link layer or a level 2 device. Well, you'll appreciate these distinctions a lot more by chapter 5 or 6. Okay? But these are technologically distinct components providing internet service to nodes in the house. So a modem, a router, a wireless, possibly a wireless access point, and then end devices, the edge that's actually connected to this home access network. Yeah.
So if the wireless access point and the router are combined, then it actually is a router. Can you see the wireless access point?
Sorry, can you repeat the question?
So you said the wireless access point and the router are like combined sometimes.
Yeah.
So sometimes when you see like the wireless access point, it is a router, or is it anymore?
Yeah, in those cases it is. The more common configuration is that the cable modem, this is actually the most common configuration. The cable modem is a separate box from an Ethernet switch to which it's connected that also has an IP routing component inside it. And if you want wireless on top of it, you connect it separately. But yeah, if these two are combined in one box, then it's actually three things. It's an Ethernet switch, it's an IP router, and it's a Wi-Fi access. These terms, I think it's hard to appreciate what technically these terms mean, but like I said, towards the latter half of the course, you will actually understand what layer these devices are operating, what protocols they're speaking specifically. For now, just try to absorb terminology, even if you don't quite understand the nuances of what a switch versus a router versus an access point mean. They're slightly different things. They're concretely different things. Okay, so let's look at some examples of wireless access, further examples of wireless access networks in more detail. We're already familiar with Wi-Fi. Wi-Fi is a shorter range technology, so 802.11 is the IEEE standard that specifies, just like Internet RFC specified protocols, IEEE standard specifies some of these Wi-Fi-like protocols, right? And others, LTE, 5G, and so on and so forth. So 802.11, A, B, or G, or N is sort of the more recent, most current generation. These speeds have been evolving over time, so Wi-Fi is already well into the hundreds of megabits per second. Hundreds of megabits, millions of bits per second speed. I don't think I've seen gigabit Wi-Fi access points yet, but I wouldn't be surprised if we're already there. Okay? These things evolve as we speak, right? By months and years. These two are the most common wireless access technologies. Wi-Fi for shorter range networks like a home network. It could also be an institutional network like here, compared to cellular networks, LTE or 5G, which is the most current or most recent generation of cellular networks, that are providing longer range wireless access. So LTE access points or LTE towers or 5G towers, cellular towers, may be located, may have a range of sort of around a mile or something on the call, but longer and shorter, depends on a lot of design issues within the network itself, right? So some places they could extend to longer ranges, tens of kilometers. You don't normally see ranges more than tens of kilometers for cellular, right? You need something different. You need an even longer satellite-based connectivity if you cannot be within a few kilometers of a cellular access. The speeds in cellular tend to be lower than Wi-Fi. So tens of Mbps today is more common for most LTE and 5G plans compared to Wi-Fi, of course, that goes to hundreds of megabits per second. But really, it doesn't matter so much because the distinction doesn't matter so much for most of the applications we use. For example, for a Zoom call, really a couple megabits per second is more than enough. For a telephone audio call, tens of kilobits per second is plenty. That's all you need for an audio call, right? The most basic phone line call encoding takes only about 30 kilobits per second, for example. So for most applications, tens of megabits per second these days is plenty. And then even if you have more bandwidth than that at the access, there might be some points in the core of the network that needs to become a bottleneck that cannot give you, let's say, 5 Gbps or 10 Gbps speeds, even if you have access network connectivity of that nature. For example, at UMass, our access network connectivity is at least 10 Gbps. And some departments, some labs have 10 Gbps coming all the way inside. But it's not like they try to download a file, they'll actually transfer it at that rate because the bottleneck may be elsewhere in the network, not at the edge. Very common, more often than not, or commonly, the bottleneck tends to be at the edge of the access network. They tend to be the weakest. Okay. So that's an example of an enterprise network like UMass. What's the distinction between an enterprise network and a home network like I showed you a couple slides before? Well, one is of course the size or the scale. It's much larger. You also see a couple more of these switches, these Ethernet switches that are connected to what's called a border router that connects to the core of the internet. There could be more than one of these routers. There's the one with a cross, circle and cross. That's the router symbol. And the square boxes with the crosses is an Ethernet switch. So at UMass, we have a few routers like this, and a pretty large number of powerful Ethernet switches. Multiple ones in every department, and they're all switched together into a network, pulling in multiplexing all the data and sending it out to the network, and then multiplexing, demultiplexing are also terms we'll encounter more. It refers to combining versus sorting out and sending to the respective destinations, respectively. Okay, Ethernet speeds keep evolving. I'd say the state-of-the-art Ethernet is more than even 10 Gbps, it's actually 40 Gbps these days. So Google data centers will be using at least 40 Gbps. The fastest ones are at least 40 Gbps switches. To make switches that are faster and faster, that itself is an art, and of course, a science in itself. Often they are put together using commodity switches that are slower. So you may put together a 100 Gbps switch to a network of smaller 3 Gbps switches. We'll look at a little bit into data center network design, probably just one class or so at most, into how powerful local area network switches are designed and deployed in practice. compared to Wi-Fi, Ethernet is much faster. Just wired networks in general is much faster than wireless. Wireless networks, you have to think of them as sort of comparable to real estate. There's a very limited amount of spectrum available. All spectrum is being used for something or the other. A lot of it is used by military, for example, for their communication. A good amount is used for TV, a good amount is used for cellular. There are very specific bands that are allocated for Wi-Fi communication. And then as you go, and some for radio, like AM, FM, and so on. So there's only a limited amount of spectrum. It's like the air around us. You can use it for a limited number of purposes. The number of frequencies is technically infinite. You keep on increasing frequencies from kilohertz to a megahertz to a gigahertz to a terahertz and so on. But as you go higher and higher in the frequency, which refers to the frequency of oscillation of the sinusoidal wave, the electromagnetic wave, it tends to dissipate sooner and sooner. So it can't penetrate walls and bodies and so on. It's shorter and shorter range. So if you want longer range communication, like AM, FM radio, they can go a long distance. They're in the kilohertz bands, the radio bands. You only have a limited amount of spectrum. That spectrum, those bands are also, the width of those bands determine how fast data can be transmitted on those. That's what's called band. Okay. That's all. Yes?
Do different spectrums have a difference in the speed that they can transmit data, or is it just the distance spectrum?
It's the distance. The speed depends on the width of the spectrum. So for example, if you have Wi-Fi has, when you say 2.4 gigahertz Wi-Fi, right? This is something you saw, well, not in this slide, but if you open chapter 7 of the textbook now, in the 8th edition, you'll see, it'll teach you a lot about Wi-Fi in great detail. So 2.4 gigahertz and 5 gigahertz are two frequencies where Wi-Fi operates. When we say 2.4 gigahertz, what we mean is a band around 2.4 gigahertz. So 2.4 gigahertz plus a few 20 Mbps channels after that. So it's around 2.4 to 2.5 gigahertz is where 2.4 gigahertz Wi-Fi refers to. So the width of that band determines how much Wi-Fi speed. Who decides what can send, what device can send at what frequency? So what if you start sending Wi-Fi information just because you wanted a really fast home network on channels or frequencies that are not meant for Wi-Fi, like on cellular band frequencies or AM FM radio? Who decides who gets to use what bands? Who decides that these are for military purposes? These are for AT&T, these are for Verizon, these are for Wi-Fi. Yeah?
This is the FCC.
Yeah. You pick up any electronic component, electrical component even. Behind you will see some specs that are mandatory, that are required by FCC. That body, it's a regulatory body that decides who gets to transmit on what frequencies. So in your home network, at short ranges or low power, if you transmit signals that conflict with cellular or radio, AM radio, nobody's going to know because it's not even going very far, right? But you can't really use that for wide area communication because it would be illegal and there's a regulatory body deciding who gets what spectrum. The cellular carriers like AT&T, Verizon, Sprint have sunk billions in options buying up spectrum so that they can resell it to you and charge you and me, $50, $100 a month or whatever they do to recoup their sunk cost in the CapEx, capital expense cost. Right? Okay. Other general, we're sort of in these are like general knowledge topics really, familiarizing ourselves at very high levels with different kinds of companies. So if you have any sort of curiosity, driven general knowledge questions about how this technology or that technology works, I don't promise I can answer, but I'll try. It's something that we're going to look at in more technical detail anyway later in the course. Okay. Anything? Okay, let's move on. So I'm finally ready to formally introduce what transmission rate or what transmission speed refers to. Transmission speed, like I said, it's measured in bits per second, right? So here there's an example of a network or a link, a single link that says the link transmission rate is R. So R is the quantity that's being measured in bits per second. What does this R mean? This R, bits per second, 10 Mbps or 100 Mbps or 1 Gbps, 1 billion bits per second. What this refers to, or what this determines, is the amount of time it takes to stuff a packet of a given size onto that wire. So transmission rate is the determining factor for what's called transmission delay. If you want to stuff a packet that is L bits long on a wire that has a transmission speed of R bits per second, then your transmission delay is L bits over R bits per second. That has the units of seconds, L over R seconds. Right? Bits divided by bits per second. Why did I say it's the amount of time to stuff a packet onto the wire? Because that's precisely what it is. The mental picture you want to have is at this point, this packet of size L is being transferred from the machine here onto this end of the wire. It's not yet gone anywhere, it's still at this end of the wire. It'll then propagate at the speed of light to go from one end to the other end. That's a different delay. Okay, we have a different name for it, that's called propagation delay. There's at least 4 different types of fundamental delays in networks, and we'll look at them. Right now, we're looking at only one of them, transmission delay, because it relates to a metric that we're all familiar with, the transmission rate, or more commonly then, or the speed. When we say speed of a network, this R bits per second transmission rate is what we're talking about. Okay. A little bit about the link layer or physical media. Bits are what propagate on the wire. Bits are encoded into electromagnetic signals. So these are like the sinusoidal waves. We're not going to look at the physical layer, but the physical layer is the one, the fifth or bottommost layer, the one that deals with encoding 1-0 bits and packing into those signals. Right? These physical media could be guided or unguided. So they could be guided media examples or those are like wires or cables, right? Unguided would be media that allows signals to propagate through space. So in Wi-Fi, it's not guided along a specific direction. So a Wi-Fi access point, when it communicates like ripples in water. So it uses the entire space around it to communicate. But if I'm running an Ethernet cable from my computer to the wall, that's all the space it's occupying. You can run as many cables as long as there's space in the room. Like each one of those is getting 100 Mbps or whatever is the Ethernet speed. But with a Wi-Fi access point here, 100 Mbps Wi-Fi access point, the whole room is getting 100 Mbps, that's it. You can't put another access point on the same frequency band because they'll conflict, nothing will get through. This is the problem of multiple access that we will look at how that's solved in the link layer chapter, right? So twisted pair is like you see there, the common technology for Ethernets, the Cat5, Cat6 is just next generation technologies. Coax cable, this is something we've seen in the cable modem example. The nature of these fiber optic is even faster because it's just carrying and bending light along the direction of the cable. These are all different cabling technologies. Fiber being the fastest of these. All of these, yeah.
Is there ever information loss either in the encoding as a way to solve or in transmission?
Yeah. It's a very good question. when bits are encoded into signals, those sinusoids, they have to be recovered, they have to be transmitted on the channel. It could be a wired or a wireless channel. And it has to be recovered on the other end. In the process of sending signals over a medium, wired or wireless, there's always loss. These signals are literally sinusoidal. These are electromagnetic waves. They will attenuate, they will reduce in intensity as they go through media, especially like walls and obstructions, like buildings and so on. They will decrease in intensity. So a signal that's sort of going like this is going to sort of become like this. The amplitude of the signal that determines the intensity is going to reduce. That will reduce the ability to recover the bits that were converted to those signals in the first place. So there is inevitably going to be loss in the medium. If there's a lot of attenuation, there will be a lot of loss. In wireless, there's other reasons like multi-path reflection from other places that causes loss, interference, multiple people talking at the same time. And this is the problem I said we're going to look at in great detail, how to solve the multiple aspect problem to prevent these kinds of conflicts. So there'll be loss. Loss is just a curse of networking. You have to deal with loss. We will look in great detail at how to deal with loss at different layers, how TCP, the reliable transport protocol of the internet, deals with loss. How at the link layer, corruption of bits is discovered or detected. In some cases, it can also be corrected by adding some, what's called as some error correcting information. It's more common to try to correct bit errors at the physical layer, that we're not going to see much detail in this course. At the layers we are going to see, which is the link layer and above, we're more satisfied usually with detecting whether some corruption happened on the way. Having a fairly good, but not 100% reliable detector. If you detect that something is wrong with the packet, you just discard the packet and hope that retransmission will happen. If it was important, somebody would retransfer it. We'll look at what this means in different contexts. It happens, whether there's reliability, how that's implemented is different at different layers, the TCP layer or the network layer. But all media lose information. Okay. All right, so this is all mostly general knowledge stuff. I'm going to quickly skip over so we have a little bit of time to cover circuit switching and packet switching. There are two paradigms, fundamentally different paradigms of how you can organize or you can design a network, a communication network. Those are packet switching and circuit switching. Okay. The internet is an example of a packet switched network. So here, we know that the network, we understood the network core as being that network of networks we're talking about, that's switching. It's carrying packets from one of those switches or routers to the next one and determining where an incoming packet needs to go next. Right? What is a packet? A packet is simply a chunk of data. When you have a big file to transmit, you chop it up into little pieces. Those little pieces are packets. Okay. If you're doing chat, like messaging on WhatsApp or something, your entire message is carried in just one packet. If it's a big file, it can be chopped up into smaller sets. Routers are happier dealing with well-defined, limited-sized sets. If you throw an entire file at a router, it's not going to be handled. So that's why you want to chop it into small pieces. It makes their job a lot more efficient. A packet switch network takes pieces of data or packets and transmits them one hop at a time. At each hop, using the entire transmission rate of that link, so that R bits per second. So if I'm transmitting, if I'm stuffing one packet at this end of a wire, that's all I can do. I have to be done with it and then move on to the next packet. I can start shoving the next packet at the same speed of R bits per second as soon as I'm done with the first, even though the first may not have reached the other end. It'll start propagating. As soon as I'm done shoving the first one, I can start shuffling the next one. I do one packet at a time at the floating line rate. That's a packet switch network. So here's a slightly more complicated example. Just 2 hops instead of 1 hop compared to the previous example. In this case, you have 2 computers that are connected by a 2-hop hop. So there's 2 links here of I believe identical transmission rates, or bits per second each. So this could be a 10 Mbps link followed by another 10 Mbps link. And let's say the first end host has a packet of size L to transmit to the second end host. How much time is it going to take to go from the first end host to the second end? In this example, transmission rate is determining all of it, like this. In a real network, there's other sources of delay that we haven't yet seen, but will very shortly see. The transmission delay at the very first hop, so that's the amount of time it takes this host to shove a packet onto this end of the wire. That's L over R. Okay. This router must wait for the signals that are encoding the bits in that packet of size L to entirely arrive here before it can start, again, shoving the bits back on this side of the link. So that's a packet switch network. You wait for an entire packet to arrive. You can't, as soon as the signals encoding the first few bits of a packet arrive, you can't do anything with it. You have to wait for the entire packet to arrive. Do some checks like, is it corrupted? Am I better off just dropping the packet right here, or should I continue with it, and so on? Everything looks good. You're then going to take the packet and dump it on the next thing. Yeah.
Curious, why can't you send bits of packets without, so if you don't have, I don't know if this is a word, but so if you don't have all the packets, why can't you just send like what you do have and wait?
Yeah. What's your name?
Natan?
Can you say that again?
Natan?
Natan. So Natan's question is, why can you not do that? Why can you not take it? Why can you not just pipeline the transmission? Like, as bits are coming here, keep sending bits there, pipelining is a good thing. In architecture, it does wonders. Why do we do that? Well, the file as a whole is being pipelined, as some packets are coming here, some packets are going there, if it's one of the packets. But your question is, it's a good question. Why don't they do this for one packet? Well, for one packet, you in some cases, you may not even know what bits to transmit over to the next wire. Or actually, before that, you may not even know which next link to transmit it on until you've gotten the whole packet. Why is this? Suppose in this example, there's no choice. This example is exactly one outgoing direction for the router. But let's say you had a router here, a host, or the names for the host. So I'll just call it. Right? This is your access router. And here's Google. And here's Facebook. That's the rest of your internet. When this router gets a packet from you, how is it going to determine whether that packet is headed towards Google or towards Facebook? It may also be connected to other places. This router may have a total of 4 ports, 3 of which are facing the wide area network. In order to determine where to go, it has to look at the headers of the packet. Okay, and depending on the encoding, it may not be able to start doing that until all the bits are right. In some cases, that is possible, and those optimizations are done. But it's a lot simpler for modularity and separation of layers to organize it where you select the entire packet, look at the headers, also get the opportunity to do header detection, so that if something is wrong with the packet, it doesn't have to go all the way or go somewhere and get dropped. It'll get dropped right here, okay, preventing any wastage of further resources. Circuit switch networks, by the way, don't have this limitation. We'll look at that in a second. So it's not like we don't ever do the pipeline signal transmission. In packet switch networks, we don't. Okay, so what's the total transmission delay? L over R was encountered here, just here. We did not, in this example, calculate the time it took light to go from here to here. So assume this is a very short cable, like a meter long cable. So light doesn't take any, well, light takes negligible time here to go from one to the other. And the total transmission delay is going to be 2L over R. So if L is 10 kilobits, R is 100 megabits, you get L over R. So 100 megabits is a fairly common commodity Ethernet speed. 10 kilobits is a fairly common packet size, which corresponds to about 1200 bytes. Right? 1200 bytes is a fairly common. So that will take 0.1, do the math, 0.1 milliseconds. So that's 1/10 of 1,000th of a second. That's the transmission delay. Yeah.
So is R determined by the device that's sending out the packet, or is it always the same within the network?
What's the ladder of?
Like, can R be different, like, between these two?
Yeah.
Like,
It could be R1 and R2. If it were R1 and R2, oh, so that was the intent of your asking what is determined by the device. Then your total delay is going to be simply L over R1 plus L over R2. Okay? L over R1 to shove it in the first. So what determines, yes, it is the encode that determines the transmission speed. Specifically, the encode we have what's called a network interface card. So on my computer, I don't even have on MacBook Pros, which is my computer, they don't have Ethernet ports anymore. So Wi-Fi is the only option. There's a Wi-Fi card in there, and that's a NIC or a network interface card on the device will determine how fast or what bits per second transmission rate that device can send out on the wire.
What about the time it takes to leave the wire and enter the destination device?
So you mean go from this end to this end?
Well, what if it's like, so, what we're talking about now is like the time it takes to stuff the packet from the device into the wire.
Right.
What about the time it takes to stuff the packet from the wire into the device?
Good question. Surprising, I've never had this question before. There is no time lost. Why is this? I mean, this is how cables work, is the best high-level answer. Let me try to break it down a little bit further. When you're putting signals on the wire, it does take, you can see why it would take, if the definition of the speed is basically that it's going to take this much time to put elements on that wire. Okay. On the other side of it, you're just getting signals. Once you put those signals on the wire, they're going the speed of light. Okay. On the other side, you get those signals, you decode those signals. There is no act of encoding them and putting them again on the wire. There is no cost for simply receiving those signals.
Isn't the decoding not a cost?
That's not transmission. I know this is not satisfying, but I don't have a more satisfying answer. This is how it works. You don't need to do that on the other side. Maybe one way to think, so let's see if I have an analogy. Yeah, okay, so here's an analogy. Suppose you have a bucket of water and a thin pipe along which you're trying to send it. It is going to take you, if just a drop of water it takes you, assume that this pipe can transmit even like one drop of water per second. It's not going to stick because it's hot. If you have a small amount of water, you just throw the whole, you say a cup of water, you just throw everything on this side of the pipe and it immediately starts flowing over to the other side. But if you have a bucket or a drum full of water, it's going to take you some time to empty the entire container, your bucket or drum, on this side until the last drop leaves the bucket and lands on this side of the wire, on the pipe. But there's no delay on the other side because it's just flowing at the rate at which the pipe is carrying it. There's no delay to recover that water on the other side. It's just once it's set in motion, it's flowing at the rate at which the piping and water. So it's a very similar analogy. It's an analogy at best. It's not a perfect analogy. Okay, so that's similar to the physics of what's happening. You've paid the cost of the bottleneck already at this thing, so it doesn't hurt much. Good question. More questions? Okay. In packet switch networks, because you're dealing with one packet at a time, transmitting it fully, you can have queuing and loss. Right? So somebody asked about loss. Loss can happen in any kind of network, including packet switch networks. When you're sending packets on a link, if the rate of arrival of packets exceeds the transmission rate of the link, then you're going to have queuing. If at a cinema, at a theater, customers at movie time arrive because the movie is popular, all of them arrive for the last 5 to 10 minutes just before the movie, there's going to be a line, there's going to be a queue. Because the processing speed of the person at the ticket counter is limited. They may be able to process one customer, let's say, once every 30 seconds to a minute. So if there's 10 of them, it's going to take 5 minutes or 10 minutes to process all of them. And so if the arrival rate exceeds the rate at which they're being processed and let in, there's going to be, this happens in packet switch networks. It's not a problem in circuit switch networks, which we'll see. So packets can get queued up. Queues are simply data structures in switches or routers that hold a bunch of packets until it's their turn to be transmitted or shoved onto this end of the wire. However, if for an extended period of time packets keep arriving at a rate faster than you can send them on the wire, right? This is the amount of time it takes to send one packet, shove one packet on the wire. So you can send the rate at which you can send packets of size L on a link of rate R is R over L. That many packets per second is what you can send on that link. And if that is slower than the arrival rate of packets, there's going to be queuing. Queues are just data structures and memory data structures inside these routers. If the amount of buffer space or memory at the router to hold this queue of packets fills up, loss is going to happen. So if I have a buffer of 100 packets, I can temporarily absorb surges in packet arrival rates that cause a queue of no more than 100 packets. The 101st packet to arrive at that full queue is going to get dropped. The router is simply going to say, I have no buffer space. So queuing can happen. Queuing beyond a certain point can induce loss. This loss is different from signals just fading or weakening while getting transmitted on the wire. That's happening at an even lower level. That's happening at a physical level. This is happening at the next level, the link level, where the bits per second speed of the link is not sufficient for the packet arrival rate. So we're in bit line, not in signal line. We're talking about queuing and loss. I keep using this term router that's doing what's called as a store and forward. It's taking a packet, it's temporarily storing it, reading the headers, checking whether it's okay, and then forwarding it to the next line. A router has two key network functions. One is called routing, which is the problem of determining a path. How do you get from your home, from your computer, all the way to Google? what's the route your packet should take across a wide network. That's the problem of routing. It's similar to going to Google Maps and trying to figure out what the route is to go from one place to another, right? That's not the only function of a router. A router has two functions. One is routing, the other is forwarding. Routing is a global action. It looks at a global picture and says, okay, to go from this point to this point, I need to take this route. In order to take this route, I need to take all packets. Let's say Google has an IP address 144.28.0. If a packet comes here with that destination IP address, this router is going to say, aha, this packet is destined to Google. I know what the route to Google is, and therefore I must send it on this outgoing port and not here or here. That's the action of forward. That's accomplished using this forwarding table that says, if a packet is destined towards Google, like that 144.28, oops, sorry. Let's pretend this is 144.28 or something. We'll look at the structure of all of this in much more detail. Then it needs to go on outgoing link 3. So let's number 3, let's number this. 1. So that's a forwarding table that keeps track of local actions. And this forwarding table has come into existence or has been populated with a global action, which is a routing algorithm or routing protocol that has computed shortest path to go from one place to another place. So that's what's happening at every point in this network. So at this router, for example, if it gets a packet destined towards this destination, it's going to take that packet, decide that that's going to be put on this link as opposed to this link. And to put it on this link, it's going to take that transmission delay that overall. So that's, in a nutshell, in basic 5, almost 10 minutes, an overview of how packet switching is working. Chop data up into small pieces. Each piece is transmitted by each node on the next outgoing link. And that's the delay that's being. Along the way, queuing delays can happen, loss can happen. Yeah.
Does the route that the packet is supposed to take, like from start to finish, does it get updated like at every router it goes to?
Yeah. Routes on the internet do change. They change slower, on the order of hours, sometimes days, sometimes minutes. Routes or paths don't change rapidly. So it's possible, but quite unlikely for different packets from your home to Google to take different routes. It's possible, but unlikely. So they change slowly.
You mentioned that a router can deduce whether or not a package is corrupted. How does a router differentiate between a corrupted and an original packet?
So it first gathers all, good question, what's your name?
Raghav?
Raghav. Oh, what's yellow hat, what's your name?
Carlos.
Sorry?
Carlos.
Carlos, yeah, I remember. Raghav's question, what's the question? Error detection. How does the router determine whether a packet is corrupted, whether it should drop it or whether it should continue forwarding it to the next hop? Well, remember I said it has to first wait for the entire packet. It waits for all the bits in the packet to come. And then it computes what's called a checksum, which is a code that is computed, a function that's computed over like a hash function that's computed over the bits of the packet. And that hash is also inserted in the packet itself. They could both get corrupted. That's why it's not an exact process. It's with high probability, but not 100% probability. It has a pretty good guess of whether the packet's corrupted. If the checksum doesn't match, it's going to corrupt. We'll look at all of this in more detail. TCP does it a certain way, IP does it a certain way. The link layer does it in a different way. Yeah.
How does the header table get updated? So if there's a new website, how does it know to send this packet to a new website?
Packets on the internet, all packets in the header, all internet packets carry what's called an IP header. It's IP stands for Internet Protocol. The IP header has very little information. Much of it is two IP addresses, the source IP address and destination IP address. Packets don't carry names like www.google.com. That's the name of the web server. Packets don't carry names. Packets carry headers. IP addresses. So they'll carry an IP address like Google's web server's address. And each router maintains forwarding tables that says, if the address starts with these bits, go here. If the address starts with these bits, go here. It's sort of like saying, it's a little bit like postal addresses, where you first route at the country level, then at the regional level, and then at the local county or town level, right? Similarly, IP addresses have structure in them. The first few bits are the most important bits. They tell you sort of roughly where they are, and then the further and further bits, the less significant bits, the more rightward bits are going to narrow down where exactly you need to go. So the IP address is the information that's being used. The destination IP address specifically is the information. It's a piece of information that's contained in every packet on the internet. That's what it allows the router to determine which
If the network is added a new router, how do we establish the new forwarding table? How do we initialize that?
Yeah, good question. Networks are not static. Routers don't get added and removed all the time, right? That's a less frequent process, right? Probably in the order of, I don't know, days, weeks, months, and so on. But we do need to address that problem. When a new router is added, a single network like this, so let's pretend this is the AT&T network, okay? It spans all of North America. Actually, yeah, pretty much, not just the US, but much of North America, because it's a large tier 1 ISP. In their network, if they're going to add a new router at a new point of presence, or a POP as it's called, because they want to expand their presence in one more city somewhere, right? Then they're going to add one or more routers there. And the routing protocol, the routing algorithm, that's the global action, that's a distributed algorithm that's executing in all of the routers. That is going to both detect the presence of a new router and update their shortest paths so that if a new router has been installed here in this network, it allows for a better path to go to Google. They will automatically recompute their paths and repopulate their local forwarding tables to be able to get you these better paths. What are these routing algorithms? People from algorithms courses remember Dijkstra's shortest path algorithm? That's an algorithm that's used in large networks. So large ISP networks are going to use an algorithm like that. That's a type of routing called linked state routing, which we will look at in much more detail in chapter 5. Yeah.
Okay, so do the ISPs control all the routing tables and all the routers of the network?
Across just their own routers.
Yeah.
AT&T may, we'll see at the structure, which is part of chapter 1. AT&T may peer with Sprint, and they may have many peering points of interconnection at Boston, NSF, and Detroit, and so on. But each ISP, each network, in this network of networks, we have a few minutes, I have a few people sitting up. In this network of networks, each network is a company or an institution like UMass that has administrative autonomy only over its devices, not over others. Packet switching contrasts with circuit switching. Circuit switching is the older technology from the days of telephone. It's been around for over a century. Unlike chopping up data into small pieces and sending one packet, call a packet and sending it one packet out at a time, circuit switching chops up the wire or the resource itself, the channel or the cable. And it sets up lanes for different connections. You cannot talk about circuits without also talking about connections. You don't talk about one packet at a time. You talk about connections, like a phone call connection. It's not one packet going at a time. It's as if a lane along a highway has been reserved for one line of communication. So each phone call gets its own lane along the highway. It's completely reserved just for that phone call. So if you make a call, you literally get a piece of a cable, maybe a slice of a cable, or multiple cables along the way, from one end to the other end in the circuit switch network. It's dedicated for you. You will not be sharing any data belonging to other phone calls. If you make a phone call and you just stay silent, nothing is being transmitted, just white noise that's auto-generated anyway, you'll still hog up your lane in the highway. Nobody else can use it. It's dedicated for you, for your call. There's no scope of queuing or loss. Once you start a call on a landline, on a traditional landline, if you start a call, you're in the network. After that, there's no queuing or loss. You don't experience long delays like you do on the internet in circuit switch networks. Your call may get dropped if you're using a cellular phone because of wireless reasons, right? Because wireless is flaky. But I think traditional landlines, calls are really robust. What's the downside? When an earthquake happens or a terrorist attack happens, a disaster scenario happens, you can't get a call through. So that's where queuing is happening in circuit switch networks. Once you get in, you get a lane all for yourself. There's no scope for queuing. But in order to get inside the network, you're admission controlled. If there's limited resources, you can only let so many people in because you only have so many lanes in the highway. Okay. So this results, the downside is idle, resource idling when you're not using all the resources assigned to you. But the upside is guaranteed bandwidth, predictable bandwidth. Other downside, the admission control, you're not able to get in at all. In the internet is very rare. If it's up, if activity is working, it'll never say, oh, there's too many people, I can't let you in. It'll say, come on over, but your experience will just suck, right? That's the difference between a reservation-based, dedicated, circuit-switched, telephony-like network and the internet packet-switched model. We'll do some math in the next class to make sure we actually understand technically how to do it. Right? Lab 1 is out. See you next Wednesday.